Welcome to Lab 3, Black Hole Orbit. The purpose of this lab was to analyze a star's motion to find the net force on the star and calculate the mass of the black hole that is exerting the force on the star. It was concluded that the mass of the black hole is 3.37 times 10 to the 31 kilograms. In finding the mass of the black hole, it can be assumed that the net force on the star is only due to the gravitational force from the black hole. The fundamental principles associated with this lab include the momentum principle and Newton's second law. The position data for the star was provided in a CSV file, and the Python code was able to calculate in the while loop the velocity and momentum for each time interval of 86,400 seconds. These values were then used to calculate the net force. The net force was calculated based on the assumption that the gravitational force from the black hole was the only force acting on the star. The mass of the star was given to be 3.5554 times 10 to the 27 kilograms, and the position of the black hole was given by the position vector 5 times 10 to the 10, negative 1 times 10 to the 10, 0 meters. This position can be subtracted from the star's position at each time interval to find their distance, which is used to calculate the net force. Big G is a constant equal to 6.67 times 10 to the negative 11 newtons times meter squared over kilogram squared. The momentum principle can be used to find the net force on the star. The momentum principle tells us that Fnet and dp/dt have the same vector components, but when they are evaluated separately, they are different quantities. Fnet can be calculated by adding up all of the forces acting on an object, while dp/dt is calculated based on momentum. In this case, with curving motion, the parallel component of dp/dt equals the parallel component of the net force. dp/dt parallel is associated with the rate of change of the magnitude of the momentum, and it is calculated by d magnitude of momentum dt times b hat. With curving motion, the perpendicular component of dp/dt also equals the perpendicular component of the net force. dp/dt perpendicular gives the rate of change of the direction of the momentum, and this can be calculated by the magnitude of the momentum times dp hat dt. dp/dt parallel and dp/dt perpendicular add up to equal dp/dt. These equations were used in the while loop to calculate the net force for each time interval. The mass of the black hole was also calculated in the while loop using the net force that was calculated. Here is a screenshot of the while loop that calculates the mass. All of the equations to calculate velocity, momentum, net force, and the components of the net force were entered in along with the equation to calculate the mass of the black hole. The mass of the black hole equals the magnitude of the net force times the magnitude of the distance between the star and black hole squared, divided by big G times the mass of the star. The mass calculated varied slightly for each time interval because the net force varied for each interval due to the star's changing position. The star orbits the black hole in an ellipse, and at some points the star is closer to the black hole, resulting in a larger force than when the star is farther away. The mass of the black hole was calculated to be 3.37 times 10 to the 31 kilograms with slight variation. The model was able to accurately predict the mass of the black hole even though the true mass does not vary. The mass varies in this case because it is calculated based on observational data. If another black hole replaced the current black hole, the mass of the new black hole would be calculated to be the same as the mass of the current black hole, because the equation only accounts for the position of the black hole. If the new black hole has the same position, you would not be able to tell the difference between masses for the two black holes.